Well, I'm excited to be here. This is our our first time to be able to talk publicly about the Groq chip and our first product. So I'm a product of the startup. This is my first startup environment, and Jim certainly motivated this in his talk. But my background is from high performance computing, so I've taken several decades of experience at Cray building very highly scalable, tens of thousands of node systems, and brought that to bear on this new chip. And as a computer architect, we've been spending the last decade figuring clever ways of using increasingly more transistors, largely to expose more instruction level parallelism. And unfortunately, oftentimes these techniques get weaponized. And one of the things that we decided to do was to pop up a level and provide a very simple, large vector approach to solving some of the vector problems that are very common in machine learning. And to reference Jim Smith worked at Cray for many years, and I had the good pleasure to work with Jim Smith, who's formerly of the University of Wisconsin-Madison. He made a point of saying, if you got a vector problem, use a vector architecture. Well, he also said, no company has ever gone bankrupt from having a good single-thread performance. So this chip is all about really good single-thread performance and a lot of computational density. So broadly speaking, what we're trying to do is really extract as much compute density measured in deep learning ops per floor tile in your data center. And that is really getting a good return on investment, as Jim said, taking advantage of those transistors and putting them to work to do something useful. And if you start with this kind of goal of really trying to drive computational density, it drives a lot of the decisions around the implementation. In particular, it's relatively cheap to plop down a lot of ALUs that are used for fixed point arithmetic and floating point arithmetic. And transistors scale with Moore's law. And despite its rumors, it doesn't appear to be totally dead. Unfortunately, wires don't scale as nicely. And so feeding these ALUs is often a substantive problem. And what we did is had a hyper focus on batch size 1 performance, very low latency, to provide not only dense arithmetic units, but the bandwidth to drive them. So just to kind of to start by just motivating and really trying to hit these threefold motivations. Uncompromised peak performance for batch size 1 workloads. So when I say uncompromised, I mean you don't have to make compromises around throughput and latency. We consider throughput and latency to be two sides of the same coin. We wanted to provide a single chip solution that had both integer and floating point numerics on the same chip. So you don't have to buy a different inference solution than what you have for a training solution, for example. And then lastly, how can we provide predictable performance at scale using determinism? And I'll talk a little bit more about determinism in a little while. But I wanted to try to motivate the approach that we took by looking at kind of the typical conventional many-core architecture. And we've seen a lot of new and emerging architectures that are very exciting. A lot of them are they're built around 2D meshes. They're a very common on-chip topology for communication. But it's also not the most efficient. And these cores tend to be very homogeneous. And so, for example, if you look at a typical many-core architecture like a Tilera or Intel Larrabee, any number of earlier many-core architectures, they all kind of contain very similar ingredients: instruction dispatch, integer and floating point units, as well as a memory hierarchy for data cache and instruction cache, and a load store unit that handles the memory interface. And lastly, they have a network for communicating between the cores on the chip and between chips across the larger system. And what we did is we took this and thought about it differently and rearranged the fundamental units by disaggregating we disaggregated these homogeneous cores into different functional units that we call functional slices. And what that allowed us to do is to factor out a lot of the instruction control and dispatch and reduce the complexity, a lot of the complexity that would go into essentially a front-end scheduler that's executing Tomasulo's algorithm to build up the data dependencies that are necessary to provide correct out-of-order instruction retirement. And instead, we exposed additional details of the instruction set to give the compiler complete and flexible control over both the temporal and spatial location of tensors as they flow through the chip. The other really important thing that we did is we recognized the conventional 5-stage MIPS pipeline that everyone learned at their mother's knee, learning computer architecture from Patterson and Hennessy's books. We took the memory stage out, and what we did is we decoupled the access of memory operands from the execution of the functional unit itself. And we'll talk about how that allows us to have thousands of memory references in flight to be able to build a really bandwidth-rich environment for computation. And so we have these kind of two approaches, and we took the many-core approach. We fundamentally felt was very difficult to program, largely because when you carve up these many-core architectures, you end up with a tiny little local memory in each core. And often you end up with additional threads in each core to be able to try to hide the memory latency that ends up getting exposed. So we took a very different approach in providing this, what we call functionally sliced microarchitecture that effectively disaggregates all these functional units and removes the central component of a CPU. And these functional slices look like very large, long vectors. In particular, this would be like a vector architecture that has a 320 element vector length. And that 320 elements comes from this stack of tiles. Each tile implements a 16-way SIMD operation. And that is effectively, it's executed over a 20-cycle period. So you end up with 20 times 16, or 320 elements in every vector. So we get a lot of work done per unit time from relatively fewer instructions in flight. So you can think of this single core that's providing 144-way instruction level parallelism. The instruction control units are dispatching instructions north and south, and data flow flows on the chip east and west, largely east and west to take advantage of communication locality within one row. So the other thing I want to point out here is in this functionally sliced architecture, each row contains, if you look across the row, it contains a cross-section of the cores. So it has the integer unit, it has a data memory unit, it has floating point unit, it has all the constituent elements. As data flows across the chip, it's going to hit each one of those things, and we take advantage of that. So the fundamental building block of this is something we call a superlane, and it represents one row of this mesh architecture. And in particular, each superlane is exposing the 16-way SIMD operation. And like I said, there's 20 of them in one slice, and that's what forms the 320 element vector. So what we did was we exposed to the compiler additional information through the ISA that includes the entire contents of a 220 megabyte scratchpad SRAM. So we've got this very large shared SRAM that everyone has access to. All the functional units read and write to it, and produce and consume their streams. And we introduced this concept of streaming registers that are flowing across the chip in an easterly and westerly direction. So memory now has the semantics of both an address and a direction. So when you do a load in a MIPS architecture, for example, say you want to load some address into register 3, you can come back 2 weeks later and the contents from that load are still in register 3. In this architecture, when you do a load of a vector into a stream register, it's flowing. And so the next cycle, it's moving, and it's moving across the chip. And how we take advantage of that is it exposes essentially data flow locality. As you're moving operands from one functional slice to another, you can take advantage of that locality and operate on it. Let's just pop up a minute and look at a conventional CPU and a memory hierarchy and think about what happens when you implicitly issue a load or a store. When you issue a load and it goes out and it misses in the cache and it ends up at a DRAM controller, and then it moves the data from the DRAM to the last level cache, from the last level cache to the next level cache. 3 moves later, you finally have it in your register file where you can actually do some operation. And that's a lot of data movement to actually have done nothing with it. And in worst case, it gets evicted and you have to do it all over again. So we want to be able to move data across the chip and actually operate on it efficiently. And so kind of the conceptual model that goes along with this Superlane, you can think of this Superlane as really a big conveyor belt for tensors. And tensors are a fundamental data type that the hardware supports natively, either rank 1 or rank 2 tensors. So you can think about it as when you do a load and you're going to move data from one functional unit to the next, it's going to pick up the tensor off this conveyor belt, operate on it, and put it back into the streams. And so as soon as it does, and it's shifting and moving across the chip. I feel like I'm explaining an architecture by kind of interpretive dance here, but it's actually kind of a good analogy because our communication patterns actually look more like square dancing because it's orchestrated and it's a well-known pattern, as opposed to many core architectures where often the communication pattern looks more like a mosh pit, if you will, than something more coordinated. So this superlane is really our fundamental unit of computation, and then we have 20 superlanes on a chip, and we coordinate that with determinism. Now let's think about determinism. Imagine waking up in the morning and being told that you're just gonna, you know what time you're gonna leave your home to arrive at work. This is what determinism looks like. Who needs this, right? Flow control is a thing of the past. If it were only this easy, right? If you got up in the morning, you knew exactly when I should leave in order to arrive at the right time. And this is what we do with our tensors. When we read a tensor out of memory, that tensor is destined to a functional unit to be operated on. We know exactly how long it's going to take. So what this means in practice, this is our photo die of our 14 nanometer ASIC that is at 1 gigahertz. This is about an 800 teraopt chip, 820 teraops. Our first product is actually a PCIe board with one of these on it operating at 900 megahertz. It gives 750 teraops of int8 performance. And that's roughly 1 teraop per second per square millimeter. That is a very dense, rich substrate to work with. So there's several things on here I want to point out that are important. Like I said, we're able to take advantage of this locality as instructions propagate north and are executed in a sequential, staggered manner. And we're able to take advantage of the data flow locality as data moves east and west on the chip. The different functional units all have very specific purpose, right? We designed a new ISA that takes advantage of the tensors that the stream programming model operates on. So the chip is split into 2 hemispheres, an east and a west hemisphere. It's not biologically inspired, it just happened to turn out that way. And it's mirrored about the center of the chip. In the center of the chip, we have what we call our vector processing engine, or vector processing elements. And each lane, there's 320 lanes, each of them has 16 vector processors in it. So there's a total of 320 times 16, or 5,120 vector processors. So we're able to take something, stream it through these vector processors en route to the matrix unit, where we can do some deep learning op, for example, produce some output feature, and then return the result back to memory. Now, I want to put in perspective, this is an SRAM-only chip, and that's a good thing. Just to put in perspective our hyper-focus on low latency, we can do we have a total of 409,600 weights, essentially, on the chip for computing these 320 by 320 matrix units. And there's 409,000 weights. We can load our weights from memory and place them into the matrix, do a matrix multiply, and store the result in less time than you typically take to do one DRAM load. So less than 70 nanoseconds, you can do 400,000 weight and accumulations across the entire chip. That's pretty exciting. We think that's going to kind of turn things on its head with that hyper-focus on low latency. Now, like I said, these functional slices are very purpose-built. And what that functionally means is the functional slices themselves are not, any one slice is not Turing complete, but taken together, the whole chip is. For example, the memory slice doesn't have any add operations. It has simple things like read, write, gather, and scatter. And it has dedicated ALUs for doing effective address computation and being able to produce a very common regular patterns, but as well, it can, the memory system is dense, and it can produce a random read every cycle. So it's very, very flexible, and there's a lot of banks. So it supports very highly concurrent memory system where you can have over 3,000 memory references in flight at any given time. So the other units on here are a vector unit, and that is all the point-wise, element-wise operations. And not surprising, that's where a lot of the ReLU, your activation functions, tanh, sigmoid, exponentiation, and reverse reciprocal square root, for example, they live in the vector unit. And then we have the big 320 by 320 matrix units that are doing a lot of the heavy lifting for machine learning codes that are using either matmul for classifier or doing convolutions. So there's a convolution engine on it that takes advantage of the dense matrix operations. And then lastly, there's data movement, both on chip and off chip. So we have a switching module, we call it the SXM, and what it's used for is switching. It's basically tensor reshapes. It's taking a tensor and moving it, shifting it up and down, doing random bijective permutations, and rotations and transposes, the kind of common things that you would do in NumPy, that kind of thing. And then lastly, as I mentioned, I wanted to point out here, all those little widgets on the top of the chip and on the bottom of the chip are chip-to-chip links. There's 16 links. Each are 4 lanes wide, operating at 30 gigabits per second. So that's a total of 480 gigabytes per second of off-chip bandwidth. And on-chip bandwidth, just to put this in perspective, each memory hemisphere provides 80 terabytes per second of stream bandwidth, 60 terabytes per second of raw SRAM bandwidth. Now, one fundamental tenet of this chip is it doesn't have a program counter. It's a von Neumann machine without a program counter, which is weird, admittedly. When the chip comes out of reset, it does a synchronization. After that synchronization step across all the slices, they are completely synchronous, and the compiler maintains an invariant that ensures that the instruction control units never run dry. So you always know there's instructions that are executing, and you know exactly, deterministically, how long each of those are going to take. So one important aspect of working on tensors is taking advantage of the data parallelism inherent in tensors. And one thing that we do to take advantage of this data parallelism is to kind of crack open the tensor. Logically, we view this as a 320 element array, but we can kind of crack open that tensor to expose both temporal and spatial locality. So for example, if we look at a simple operation where we're reading a vector from memory, and we're going to flow that on the chip into our matrix, our MXM, or our matrix unit, where we're going to do a matmul or a conv2D, for example. And that flows across the chip in this kind of stair-step stagger way. And when it reaches the functional unit, we take advantage of that spatio-temporal locality when we produce a fused 320 element fused dot product all the way up this tensor. Okay? So we kind of, as the data arrives, we can perfectly zip it up and produce the result, which then flows back on the chip in kind of the reverse direction, so it can be written out to memory in memory. So you think about, we're producing, the functional slices operate as producers and consumers, and the stream registers act as a conduit between the different functional slices. So as I mentioned, there's no concept of a program counter. Instead, what's kept track of is, in essence, the global time across the system, not only across the chip, but across the system. And so, as an example, programs are scheduled, and you can see this represents kind of a spatial relationship. So you can see that it mimics the exact spatial orientation of the different functional slices on the chip. And I wanted to give an example of kind of to show what it looks like, what a program looks like in this producer-consumer environment. So this is actually the max pool layer from ResNet 50, and the solid lines here represent the data operands. The dashed lines represent the results. So for example, you can see at the beginning of time when this routine starts, we're reading our operands from 16 different memory slices, and those operands literally just kind of get passed along from stream to stream, or from hop to hop, until we've accumulated all 16 of them, and we get at our destination functional unit, where we do a transpose, and then the results flow back, and we write it out to memory. And this kind of, to illustrate how the different functional units coordinate in this very simple producer-consumer way. And the stream registers act as the conduit, providing essentially the carrying capacity to move the 60 terabytes per second of actual SRAM bandwidth. So, as I said, it's relatively easy to plop down the ALUs. It's much more difficult to feed them at full bandwidth. And I wanted to show you what the roofline diagram looks like to illustrate kind of the two regions of operation. The first region is kind of this under the sloped area of the roofline that shows basically our pipeline fill time as we're moving our operands and filling up our pipelines. It's a pretty steep line, and that's good because the slope of that line represents your memory bandwidth. So in this regime, we're limited by our memory bandwidth. And once we've saturated we're able to move all our operands into the functional unit, we are able to limit, our performance is limited only by our ALUs and the number of ALUs that we can fit on the device. So that's this upper region, this upper plateau, where we're arithmetic limited. Of course, none of this would be possible unless you can program it. So this slide kind of describes our software stack. And as just an example, we provide a number of tools to help with quantization because it supports both int8 and FP16. If you want to operate in int8, you can do that. There's quantization tools to help quantize and take advantage of the available deep learning operations that are abundant and plentiful. The other avenue is there's a Groq API, which is effectively a bare metal layer for programming the device at a lower layer of abstraction, right? So you have kind of an instruction level assembly language layer of abstraction. Upon it is a tensor layer of abstraction, and then on top of that is your neural network layer of abstraction that we've all come to know and love. Things like Conv2D, MaxPool, softmax, things like that. So one of the things one of the things I wanted to point out is really, as Jim pointed out earlier, it's all about transistors. And it's really about how we're putting those transistors to good use. And if we were to take the architecture and just think about your architecture gives you effectively how the chip is organized and the balance of memory bandwidth and basically moving data and computing on it, and how you're able to turn that into actual useful work. And if you were to just kind of divide out the number of useful deep learning ops we can get per transistor, it's kind of interesting. We get about 30,000 ops per second per transistor. That's kind of a weird number to kind of get your head around. But it's literally 5 or 6 times more than the next closest competitor, which is a very highly parallel architecture GPU, for example. And we see almost a direct correlation between that 5x factor of more work per transistor in our latency reduction. So for example, ResNet 50 executes at over 20,000 inferences per second and has a forward pass latency, a single inference latency less than 50 microseconds. It's about 47,265 nanoseconds. As it turns out, like I said, the chip is deterministic. So in the compiler, literally it says, here's how many cycles it's going to take. That's exactly how many cycles it takes, plus or minus 0. So this is the 14th chip that I've done in my career. And this is the first one that doesn't have an arbiter. It doesn't have a replay mechanism. There's no reorder buffers. Things that are reactive components, like a cache, a link level retry, those things have to be dealt with to provide this kind of determinism. And by addressing those things, what we did is effectively deal with the variance in tail latency. We don't have tail latency. We know exactly how long operations take from one point to another. There's no flow control in the chip. That's weird. That's very weird. And we're able to take advantage of it because it's software defined, and that flow control is orchestrated by the compiler. So there's no hardware interlocks, and there's no flow control. There's no stoplights, so to speak, from our earlier example. So I hope this gives you a little bit more background on kind of these 3 areas that we really sought to have uncompromised peak performance. The chip itself is able to reach a petaop at 1.2 gigahertz, so the architecture scales up to a petaop, and it provides both integer and floating point arithmetic. Okay, so the idea is we're focused on inference, but we want to be able to crawl before we run, and inference is a very logical step to be focused on. It allows us to be able to move from inference to training solutions to be able to build glueless multiprocessors that scale to thousands of nodes and be able to build out these predictable performance through determinism. You're no longer suffering the tyranny of the 99th percent tail latency. At Google, I spent a lot of time chasing down 99% tail latencies because it's critical. Your scaling is often limited by the bottleneck of the slowest link in a barrier synchronization. That's my talk. I wanted to thank you and simplify compute everywhere.
Thank you, Dennis. Very impressive. Questions for Dennis? Over there.
Hi, Dennis. I really appreciate the level of detail you put into this presentation. I feel like this deterministic architecture is like really every computer architect's dream, but it also tends to be the thing that we fall on our swords with because basically, it's a question of are the compilers smart enough to run code on this thing. So I don't know, maybe you could address that a little bit.
Sure, sure. So some of these approaches have been tried before, and really, if we take a walk down memory lane to think about EPIC, explicitly parallel instruction computation, for people that remember the 1990s. A lot of work done at University of Illinois' Impact compiler group to be able to produce very efficient code for VLIW. A lot of that work was really important and set the stage, and it really helped us to understand what some of the bottlenecks and what some of the problems were. One of the big problems is they didn't have precise state information about the architecturally visible state. In other words, they couldn't predict everything. They had to do some amount of dynamic profiling to understand how their code vectorized on that architecture. One thing we did when we made the ISA is we very deliberately exposed additional detail to the compiler, as well as things like semantics for exceptions, math exceptions. When you get an overflow condition, how do you react to that? And those kind of things are decided up front. So when as a programmer, you know how you want your numerics to saturate, or do you want them to roll over, so that you don't have to deal with exceptions that arise from it, and take advantage of that. So there's a number of things that we had to do to expose this additional detail to the compiler to make this deterministic architecture scale, not only across one chip, but across multiple chips. I don't know if that answered your question, but you really have to expose a lot of additional state to the compiler. And that's one thing that many core architectures do great, is they make a great compiler. Runs a compiler and generates it's essentially your front-end dynamic scheduler. Instead of having it done in hardware, you have it done statically scheduled on this computation graph, and you're able to emit code that really maps well to these parallel architectures.
Last question.
Okay. So I noticed in your scheduler diagram with maxpool that there's a lot of white space, which I assume is no ops being executed. So can you talk a little bit about, like, for a common model, like how much, what's the effective compute rather than the peak, and what kind of techniques you're using to improve that?
Sure, sure. So the question and the observation is, if you look at how that thing is scheduled on the chip, there's a lot of white space. Does that actually mean it's lower utilization? And the answer is yes and no. So what I showed was something at batch 1, and it's often the case. I mean, we take the philosophy of we're going to sprint to completion, right? We're going to go as fast as we can for batch 1 and get the inference done as quickly as possible. You can find parallelism within requests and across requests, right? Using batch helps you to get better utilization across that at some latency cost. So yes, does it mean you end up getting some amount of lower utilization? That's true. And Dave Patterson likes to point out kind of a corollary to Amdahl's law, and that corollary is even low utilization of a huge resource, like these large two-dimensional MAC arrays, still delivers overall speed up that is really, really positive, very good. I mean, so what we're able to do is to deal with that low utilization through aggressive clock gating, as well as sparsity techniques to be able to deal with zeros when they do arise. So there's a lot of zeros. So, great question.
Thank you, Dennis. Let's thank Dennis one more time.